So, okay, so this work was done in collaboration with Mark Wilde while he was still at LSU. Now he's in Cornell, and I'm in Amsterdam, while at the time of this work I was in Ulm. So that's why the many affiliations. Okay, so the main topic is this bosonic dephasing channel. So let's try to see what model that is. It's a model of noise for single bosonic mode, right? So let's say that you have light traveling along an optical fiber, and here I drew two different rays, and you can see that the blue ray and the red ray have different optical lengths, right? Optical paths and optical lengths. So that means that they will gain a different phase along the trajectory. And so how can you model this? Well, you can think of this bosonic dephasing channel model in which you have a phase randomization that happens with some probability distribution phi, distributed on this probability distribution is defined on the angles, right? And so here you see that there's the canonical Hamiltonian of the bosonic field, which is just A dagger A, where A is the annihilation operator. Okay. So basically, this just adds a random phase to your input density matrix. Okay. Right. So this is the channel. So first important thing to observe is that this is not a Gaussian channel. Okay. So, and the reason why it's not a Gaussian channel is because this unitary is, this will be Gaussian, right? So this is just rotations in phase space. So there's nothing more Gaussian than that. But the point is that Gaussian channels are not happy when you take convex combinations of them. And here, this is exactly what we're doing. So this does not behave as a Gaussian channel unless the probability distribution, is like trivial. Okay, so but rather confusingly though, particularly important model of specific model for a probability distribution P here is the wrapped Gaussian, so the wrapped normal distribution. And so what happens there is that you consider the angle phi to be kind of a real variable that is normally distributed, okay? And of course, since we are talking about the circle, the Gaussian there will wrap around the circles many times, so that's why here you get formally an infinite sum. Okay, so that's kind of an important model because there is just one parameter, this gamma. That's kind of the variance of this Gaussian. So the larger gamma, the more spread out the Gaussian is. That means the more noise you're adding to the system. Okay, so far so good. So let's take a step back and let's review some basics before I tell you the main result. Okay, so there is the Hilbert space is the single bosonic mode. So you got a Fock basis, okay, 0, 1, 2, all the way to infinity. And then you have this canonical Hamiltonian, A dagger A, that, acts, it's not like the eigenvectors are these Fock states, and the eigenvectors are exactly the index of the Fock, and the eigenvalues are exactly the index of the Fock state. Okay, so then density operators on the Hilbert space are naturally thought of as infinite matrices. That's good, so we'll often write this infinite matrices. Okay, so the first thing to work out, it's a very simple calculation, but let's go through it, is the Fock basis representation of this channel. Okay, so that means if you let it act on this NM ket bra. Okay, and you see immediately that since N is an eigenvector of A dagger A and M the same, right? So what you gain here is a random phase. So you get this kind of, you get a scalar here, and what you get is basically the Fourier coefficient of this probability distribution P. Okay, so basically what happens is that this input operator gets multiplied by a number, okay? Very simple. So if you want, this operator is formally an eigenvector or eigenoperator of the channel. Okay, so what about this coefficient here? So this, so first of all, so that means that the channel acts as a entry-wise multiplication on the input infinite matrix. That's good. So this is called also a Hadamard channel, because the Hadamard product is the entry-wise product between matrices. It's kind of how they taught you not to multiply matrices in high school. Okay, so and the other peculiar feature here is that this TP matrix, whose coefficients are this Fourier coefficients of P, this is a Toeplitz matrix. What does it mean? It means that the entry just depends on the difference between N and M. Okay, so the value of the entry depends just on the difference between the indexes. So this will be kind of crucial. And of course, like for the special example of the wrapped normal distribution that we saw before, what you get is, again, unsurprisingly, maybe another Gaussian. So that means you see what happens here is that basically the off-diagonal elements of the input density matrix are strongly suppressed with this Gaussian distribution. So of course, like when gamma is high, you remember the noise is large, that means that capacity will be small because this will be kind of approximated by a completely dephasing channel, right? One that kills all off-diagonal elements. Okay, so what do you want to use channels to, right? So a little review of the capacity zoo. So first task is the one that was already talked about before, send qubits. Okay, so this drawing really is kind of the standard one that you already saw it in the previous talk. When you want to send a channel M and you're allowed to do an encoding and then use the channel, your noise channel, in our case the bosonic dephasing channel, n times, and then you're allowed to do a decoding. And so and the rate of this communication is the number of qubits in M divided by the number of uses of the channel. So basically, and in order for the rate to be achievable, you require the error, the decoding error, to be vanishingly small. And the quantum capacity is just the supremum of all achievable rates. Okay, so it's a number that just depends on the channel and kind of encodes how many qubits you can send asymptotically in the asymptotic limit. Okay. All right. There is another task that may be of interest, which is that of establishing entanglement between sender and receiver. And of course, if you can send qubits, you can also establish entanglement, but the other way around is not necessarily true, because to establish entanglement, you may want to use additional resources, such as, for example, the ability of Alice and Bob to communicate classically. Okay, so that's a scheme for entanglement generation. You see, you have, again, some number of uses of the channel, asymptotically large. And then in the middle, you can do what are called LOCC, local operations and classical communication. So Alice and Bob can talk on the phone, and they have local control over the quantum systems. And at the end, you want to have like a large number of singlets. So a very large entangled state. Okay. And there are other quantities of interest, like, for example, the private capacity, in which you want to send private information, and or also the two-way private capacity, in which you want to establish a secret key. Okay, so this is why I call it a zoo. I mean, there are many numbers, and there are also the strong convex exponents. Like for people in the know, this is kind of a more so like basically they are defined in exactly the same way, but now I don't require the error to vanish asymptotically. I just require it to stay bounded away from one. Okay, so one would be the maximum error, so which the communication is completely noisy. If it stays just below one, I say it's fine, and I declare a rate achievable. In this way, I can possibly increase the rates. So, and I get all the strong convex exponents for all these tasks that we defined before. So, strong convex quantum capacity, strong convex two-way, private, two-way, private. Okay. Okay. So there are 8 quantities, and the problem is to compute them for the bosonic dephasing channel. Okay. So that's a problem, and the result is that. Well, okay, it turns out that all of these quantities are equal for this special channel, and they are given by a very, very simple formula, which is just the log of 2 pi minus the entropy, differential entropy of the probability distribution over the angles. And okay, there is a regularity condition that we require, that is basically some Renyi entropy of the probability distribution for alpha larger than 1, be finite. Okay, this is is required for technical reasons. I don't know. So basically, okay, every example you can come up with will satisfy this. For example, if P is continuous, then that's fine. But we don't know actually whether this is needed, or you can further relax it. Right. So in particular, for this channel, there are some like there's a massive collapse in the capacity zoo. So in particular, unlimited classical communication doesn't help to generate entanglement. Basically, does not enhance capacities. And also generating entanglement is exactly as difficult as generating a secret key, which is not necessarily the case in general. Okay, because like with entanglement you can distill a secret key, but the other way around is not true, of course. Okay, so in the other observation, if you want to understand why this quantity is positive, it's very easy, because, for example, one way is to write it as the relative entropy between the probability distribution P and the uniform probability distribution over the unit circle, over the angles. That's definitely positive. And there is also generalization for the multimode case, in which you like you have a multimode dephasing channel in which like something like this, but then the probability distribution is over m angles, and you have m bosonic modes. And again, the formula looks just as the one I showed you before. There's just this factor m that takes into account that you have different number of modes. Okay, and I should also observe that formulas very similar to this one were known for the finite dimensional case, for the discrete case, in which you have you can define also a dephasing channel in that case, and the formulas were proved in this paper by Pirandello, Laurenzo, Toviani, Banchi, 2017, using techniques from old paper by Bennett. All right, so well, just to look at a plot for once, which I don't often do. But so that's the capacity for the wrap normal. You see there are, well, so like the important regime, let's say, is the one for large gamma. Remember, we said for large gamma, the channel is very noisy because it suppresses very strongly the off-diagonal elements, and you expect the capacity to be very small, right? And indeed, it is exponentially small. So that's good. So it turns out that for the wrap Gaussian, you can actually compute this. There are some special functions that allow you to compute this. So you can give, for instance, known functions. All right. So now, second part of the talk, some proof ideas very quickly. Well, not too quickly. Okay, so let's say that we want to prove a kind of a minimal statement, just that the quantum capacity is equal to the two-way as given by the formula that I presented, okay? Right, so the quantum capacity is always upper bounded by the two-way, right? Because, as I said before, if you can send qubits, you can establish entanglement, but the other way around is not necessarily true. So you just need to show a lower bound on the quantum capacity and an upper bound on the two-way. How do you do this? So first of all, the lower bound on the quantum, well, the most obvious one is the coherent information, okay? So you just, again, this was defined before. You just come up with a state on AA prime, and then you send the system A prime over the channel, and then you compute a quantity, which is kind of an entropic quantity called the coherent information over the state. Okay, and that gives you a lower bound. And in fact, it's well known by the LST theorem that if you regularize this quantity, you get the quantum capacity. So if you don't know what the regularization means, it doesn't matter, because for this special channel is known to be degradable. And so that means that this formula that I'm writing on the right is exactly the quantum capacity, okay? So it's a single letter formula for the quantum capacity, so we could be happy, but of course things are not that simple, because here there is an optimization of infinite dimensional states, so we still don't know at this stage, right? But at least there's a single letter formula, okay? Fine. Okay. So remember, we have to come up with an ansatz for the state to be transmitted. Okay, so the most obvious ansatz is like this. So you take the maximum entangled state over the first D systems. D levels. Okay, so that's a D-dimensional maximum entangled state. You send it across the channel, and what you get there, you get this. If you compute the coherent information, you get this entropic expression, and this involves the upper left, the top left corner of the matrix TP. You remember this TP is this Toeplitz matrix that identifies the channel via Hadamard multiplication, and you get the D times D top left corner of this guy. Okay, so like this. Okay, so you see here there's okay, so it would be very helpful at this stage to be able to compute the spectrum of this TPD matrix, right? Because that would allow us to evaluate this expression. And how do you do this? Okay, so this is a Toeplitz matrix, you remember? So how do you compute the spectrum of a Toeplitz matrix? So that's the question. Okay, so for example, this is a Toeplitz matrix, you see? Like, so if you if you want like a picture, a graphic picture, Toeplitz means that you see the main diagonal is uniform, and then also the diagonal immediately above the main diagonal is also uniform, so all equal elements, and then the one again above, all equal elements. In this case, only one element. So that's a Toeplitz matrix. How do you diagonalize this one? It can be done for this special example, but it's not that simple in general. So Toeplitz matrices are not that easy to diagonalize. So this is, but there is an assumption that can make our life much easier, which is the observation that when B is equal to C, in this special case, the matrix becomes circulant. What does circulant means? It means that it commutes with the shift operator. So shift operator, the one that shifts the basis elements by one in a cyclic way, that's the shift operator, and T commutes with it. So when B is equal to C, the matrix is not only Toeplitz, but it belongs to a special subclass of the Toeplitz matrices, which are the circulant matrices. And in that case, the diagonalization is super easy, because you see it commutes with the shift, and so that means that it has the same eigenvectors of the shift operator, because the shift operator is non-degenerate. Okay, so and how do you diagonalize the shift? Well, this is also super well known. You just take the discrete Fourier transform. Okay, so that's enough to diagonalize it. So that's good, right? So we are making progress, but in general, this matrix here is not, this Toeplitz matrix is not circulant, unfortunately. So you can't apply all of this directly. Okay. But okay, but when is it the case that it is circulant? Let's ask ourselves. So if you kind of write down the conditions, you'll see immediately that this happens when the probability distribution P is supported on the roots of unity of order D. Then the D times D top left corner of the Stirplitz matrix becomes circulant. Again, not very surprising, kind of the only reasonable thing that could have happened. Okay, and so for that case, you can diagonalize this one in Fourier basis, and you see immediately that the eigenvalues are D times this coefficients of the probability distribution over this roots of unity. Okay. And so then you can compute this entropic expression immediately, and it gives you the log D minus the entropy of this discrete probability distribution. Okay, so for this special case, we are good. We solve the problem, and then you may hope that what happens if you take D to infinity. So then the constraint becomes that P is supported on a dense set, right, or something like this in the limit. So maybe you can hope that this constraint vanishes, right? That this covers all probability distributions. And in fact, this is exactly what happens. But to make this rigorous, you have to use some tools from asymptotic linear algebra. And the tool that is perfect for this purpose is called the Zerger's theorem. So this was proven by Zerger in 1920, and then has been refined by many people ever since. And the particular refinement that we use is due to Serra Capizzano in 2002. And so what this tells you is exactly that if you're trying to diagonalize this Stirplitz matrix, and because you want to compute the trace of some function of the eigenvalues, then okay, so then in the limit, that's exactly what you get. You get exactly that the eigenvalues are the original probability distribution P. So you can compute this limit of this trace like this. So by doing the integral over the probability distribution. Remember before the eigenvalues were D times the discrete probability distribution. So now the eigenvalues kind of in some asymptotic sense are exactly the discrete probability distribution that we started with. Okay, so in this way you can take the limit very easily in the disentropic formula, and you get exactly what we were looking for. Okay, that's kind of what's going on here. So what about the upper bound? Well, for the upper bound, there is a trick, because the upper bound on the two-way quantum capacity would require an optimization over all sort of complicated protocols. This LOCC intermediate steps. But there's a trick. There's a very well-known trick that was again devised by Bennett, as many things. And the trick is that this channel, the specific channel, belongs to a very special class of so-called teleportation simulable channels. What are teleportation simulable channels? Are those channels for which, basically, operationally, one use of the channel is the same as Alice and Bob having the choice state. So, which means that, okay, of course, if you can use once the channel, you can generate the choice state, but just Alice and Bob, Alice sends over 1/2 of the maximum entangled state, and now they have the choice state. But what this tells you is that if you have the choice state, you can generate on Bob's side the output of the channel starting from any input on Alice's side via LOCC, local operations and classical communication. So kind of this direction is obvious, so that if you have this resource, you can generate this one. But for these special channels, the two are actually equal. And this is because they have a symmetry between a special kind of covariance symmetry with respect to the unitaries that pop up in the teleportation protocol. Okay, and that's basically it. Okay. So, and using this trick, you can say that the two-way quantum capacity is upper bounded by the distillable entanglement of the choice state, because if you try to generate entanglement using the channel, okay, it's the same as trying to generate entanglement using the choice state, and then use known upper bounds on the distillable entanglement, which is a relative entropy of entanglement. If you know how this is defined, there is an optimization, a minimum over separable states, and the way to deal with it is you make an ansatz. Okay, so you make a kind of a obvious ansatz, to be honest, and what you get here is again the same limit. So when you apply again Zerger's theorem, because it's exactly the same limit, and well, that's what you get. So you get an upper bound which is exactly the same as the lower bound. End of story. And okay, it's kind of interesting from the mathematical point of view that this Zerger's theorem appears both for the lower bound and the upper bound. And it's really the right tool here. Okay, so very quickly, some conclusions. We found a formula for all the private and quantum capacities of the bosonic dephasing channel for generic probability distribution P. And well, yeah, exactly. So the right tool is the Serger's theorem that I pestered you with. And okay, so there are some interesting open problems. First of all, this is all about unconstrained capacities. Okay, so but for continuous variable channels, it makes a ton of sense to look at energy constrained capacities in which the input is forced to obey an energy constraint. And for those, we don't have formulas. So this is a very interesting open problem. And the other one is what happens if you add photon loss. Okay, so like a lossy channel, and you concatenate it, and also we don't know. And with that, I thank you.
Thank you for this very nice talk. We have time for questions. Yeah. So, well, actually, I'm going to bring you the mic for the recording. I was told we should use the mic.
Thank you. In one of the first slides, you said something about secret key generation and entanglement generation, and they are equivalent, something like that.
For this special channel, they are equivalent, but in general, of course, not. If you have entanglement, you can say always like Alice and Bob measure locally, and they have a secret key. But the other way around, of course, is not true because a secret key is a classical resource. And,
So it only applies to this very channel.
Yeah, only applies to this one. I mean, to a more general class. But yeah.
Okay, and you also have some constraint on this probability distribution.
Yes.
On the.
Yeah, exactly. Basically, that the Renyi alpha entropy has to be like this.
Yeah. So what kind of reasonable distributions are being excluded by?
Yeah, some kind of very kind of singular distribution that are very, very picked, like in an unbounded pick on some angle, for example. This kind of things.
But they're not reasonable, not physically reasonable distributions, right?
They are not particularly physically reasonable. Yeah.
All right. Thank you.
But you never know.
Sure.
Thanks for the talk. So I just want to ask, like, if you send coherent Gaussian states to the boson dephasing channel, dephasing channel, do they stay Gaussian?
No, I don't think so.
They don't?
No.
So it's like we cannot use this channel for like CVQKD or something?
No, well, you can, because as I said, like you can compute the capacity and it's non-zero most of the times. So you can, but it's just it doesn't work this way. You don't.
It doesn't work with Gaussian states.
I don't know. Maybe it works. I don't know. Like the thing is that they don't stay Gaussian, so you have to come up with something else. So
okay.
I mean, it may be that those work, but the analysis may be more complicated.
Okay, so right now what we have in CVQKD is all of the attacks and everything are just for Gaussian states. So
yeah. No, exactly. So this was one of the reasons why we looked at this, because it's the kind of like the simplest example of non-Gaussian channel that you can come up with.
Okay, thanks.
Great. Good. Another question here.
Thanks. How many of the technique, like, would you be able to, if you were interested in the continuum, so instead of looking at a Toeplitz matrix, you had some like a translation invariant kernel, would the techniques still kind of go over in the
Interesting. So, good question. I have no idea, to be honest. One should start by looking up this Serger's theorem, what they have in this more. This is a very interesting question. I have no idea, to be honest.
All right, more questions?
Thanks for a great talk. What does the optimal encoding strategy look like?
The optimal encoding for what?
For achieving the quantum capacity, one-way quantum capacity.
Yeah, okay. So, as I said, like for the coherent information, the optimal state looks like the basically very, very stretched, very long maximal entangled state. So that achieves the capacity. So.
With high randomity at some point, right? No. In the finite dimensional case, but this is infinite dimensional, so that's why I'm.
Yeah, but in the limit, that's basically what Serger's theorem is telling you, is that in the limit you can achieve this. So if you take a maximal entangled state on the input and you send it, and then this asymptotically achieves the coherent information.
Okay, cool. Thank you very much.
Thanks. So this channel is both teleportation simulable and also degradable. And do we know in general any relation between these two types of channels?
Not that I'm aware of.
All right.
No, because they somehow they look a bit different, right? It's basically, I mean, all of the channels for which we know teleportation simulability, they are covariant with respect to the unitaries that pop up in the teleportation protocol. So for discrete variable, this would be the the Wilde unitaries, and for continuous variables, the displacement operators. But this case is exactly. So in this case, it's neither of the two case. It's more like the discrete. This looks like more the discrete case than the displacement operators case.
Right. Thanks.
Do you think it would be hard to extend this to what you mentioned on your last slide, to energy constraint, like to a setting where you'd be worried about how much energy you need to implement?
So it's kind of, I mean, it's easy to derive lower bounds for the energy constraint capacities, but upper bounds is way more difficult. I mean, we tried a bit, but we couldn't go very far. But we didn't try super hard, so I really encourage you to go try it.
All right. I think it's time we let people switch auditoriums and thank our speaker again. Thank you very much.
Thanks a lot.